Hello students, welcome back to the classroom point. In our today's class, we are going to discuss the molecular orbital theory and its advantages. So let's begin the class now. Molecular orbital theory, known as the MOT. So let us try to see what is the drawbacks in the valence bond theory. Only one drawback we shall discuss. Anyhow, that was discussed in the drawbacks of the valence bond theory itself. So now, what is the necessity to propose the molecular orbital theory? So when you observe a molecule, let us take the chlorine molecule Cl2, where we know that there is a chlorine sigma bond or single bond is present. So this single bond is formed by the overlapping of the p orbitals of both the chlorine atoms. So let us see the electronic configuration of the chlorine also. Neon 3s2 3p5. So the valence electron from the 3p, one of the 3p orbital, participate in the overlapping like this. This is the p orbital of one chlorine having the unpaired electron and p orbital of the another chlorine having the unpaired electron with opposite spin overlaps with the chlorine atom and produce the chlorine-chlorine sigma bond, or we can say the single bond. So in this chlorine-chlorine single bond, if you observe, from every chlorine atom only one electron is participating. After participating in the bond formation, now the electrons in chlorine molecule experiences two types of the attractive forces. Except this electron which is participating in the bond formation, rest of the electrons, that means out of 17 electrons, 16 electrons are still feeling the attraction from the chlorine nucleus. And other chlorine atom also feel the same thing. But these two electrons are experiencing the nucleus attraction powers from both of the chlorine nuclei that is present in the bond formation. That means even though after formation of a molecule, now chlorine is having the electrons which are experiencing the two type of the attractive forces. One type of electrons are experiencing the only one nucleus attraction power, and bond electrons are experiencing the nuclear attraction power of the both of the chlorine atoms. Now we know that chemical properties depends mainly on the electrons. So when electrons are having the different type of the attractive powers, then automatically this Cl2 molecule also should exhibit two type of the properties, that is Cl2 molecular properties as well as chlorine atomic properties also, because chlorine atomic electrons still not changed. They remain as it is. Out of 17, 16 electrons remain same. But Cl2 molecule, not only Cl2 molecule, any molecule, once it participates in the, once molecule is formed, they don't show the atomic properties, they try to show the molecular properties. That means molecular orbital theory suggests that once molecule is formed, these atomic orbitals no way exist. They also convert into the molecular orbitals. So to explain that particular concept, molecular orbital theory has been proposed. Now let us see what is the main salient features of the molecular orbital theory. So according to molecular orbital theory, a molecule is formed by intermixing of atomic orbitals of two bonded atoms. So now let us take the concept. Imagine two atomic orbitals. AO stands for the atomic orbitals. So atomic orbitals of the atoms intermixes with each other and they produce new orbitals which are called the molecular orbitals. And while intermixing, what is the necessity conditions for these atomic orbitals? So atomic orbitals must have the same energy. Both atoms must have the same energy. That means 1s orbital of one atom can intermix with the 1s orbital of the another atom. Like that, 2pz orbital of the one atom can intermix with the 2pz orbital of the another atom. That means they must have the same symmetry also. So 1s intermixtion is possible. Why? Because they carry the same amount of the energy. But in case of the heteroatoms, 1s can intermix with the 2s orbital. But most of the cases, 1s orbital intermix with the 1s orbital. And symmetry in this sense, they must have the same direction. That means pz orbital intermixes with the pz orbital. That means both belong to the same orbit. And px orbital intermixes with the px orbital. And py orbital intermixes with the py orbital. That means pz orbital do not intermix with either px orbital or py orbital because their direction of lobes or location is different. So these are the necessary conditions for the atomic orbitals while intermixing. So imagine now atomic orbitals of the same energy intermixed with each other and they are going to produce the new orbitals. They are called the molecular orbitals. Then how many number of atomic orbitals are to be intermixed and how many number of the molecular orbitals are to be produced? Here it is clear that number of atomic orbitals intermixed is equals to number of molecular orbitals produced. That means if 2 atomic orbitals are intermixed, then we get the 2 molecular orbitals. If 3 atomic orbitals intermixed, we get the 3 molecular orbitals. If 6 atomic orbitals are intermixed, we get the 6 molecular orbitals. That means the number of molecular orbitals produced is equals to the number of atomic orbitals that get intermixed during the formation of the molecule. Now, the question is, after intermixing of the atomic orbitals while producing the molecular orbital, what could be the location of the nucleus of both of these atoms? Now, let us take the both approach. See, this is the atomic orbital of one atom and this is the atomic orbital. Let us imagine 1s orbitals only. Nucleus, nucleus. So, what these two theories says, that is valence bond theory and molecular orbital theory. Valence bond theory says that just overlapping of the outer orbitals is possible so that nucleus position is not disturbed. Only these common area electrons are experiencing the attraction power of the both of the nuclei, but remaining electrons are experiencing the attraction power of their respective nucleus. But molecular orbital theory never suggests like that, but molecular orbital theory says that complete mixing of both of these atomic orbitals takes place so that new orbitals are produced. They are called the molecular orbitals. When you observe the difference between the atomic orbitals and molecular orbitals, in case of atomic orbitals, the electrons present in the atom are rotating or revolving around the nucleus, only one nucleus. That's why we can say that atomic orbitals are completely monocentric because they have only one center. So once both are mixed and produced the molecular orbital, then both of the nucleus also will come so that these new electrons are now revolving around the nuclei. That means whatever the number of new atoms participating, all the nucleus will come here. So the electrons has to revolve around all the nuclei present in the molecular orbital. That means 2 or more than 2. So in this case, we can say that molecular orbitals are polycentric because they have now more than one center is present. That's why these are polycentric. And we also know that atomic orbitals are usually designated as S, P, D and F subshells. But in case of the molecular orbitals, these are designated as sigma, pi, delta, etc. So these are because we have to differentiate the molecular orbitals from the atomic orbitals. Now, the question is, we know that atomic orbital is usually represented by the amplitude of electronic wave psi. So psi has two values, positive value and negative value. Then in such cases, atomic orbitals will, whether atomic orbitals produce only one type of molecular orbitals or a different type of the molecular orbitals. So the exact intermixing of the atomic orbitals to produce the molecular orbitals is explained by the linear combination of atomic orbitals. So we shall discuss the linear combination of atomic orbitals now. Linear combination of atomic orbitals known as LCAO. So this linear combination of atomic orbitals says that an atomic orbital, we know that atomic orbital wave function is represented by the wave function psi. So let us take the two atoms, atom A and atom B. The wave function of the atom A is psi A and atom B is psi B. So when these two atoms are intermixing, so the intermixing process can be done in the two ways. That is, first one is constructive interference. So constructive interference meaning here is, this is the psi A wave function of the atom A, which has the plus, minus and plus minus signs are there. And this is psi B. So when two atoms wave functions, atomic orbital wave functions or electronic waves with the same sign intermixed, then they produce psi A plus psi B. That means the amplitude of the electronic wave increases. So this type of orbitals are called the bonding molecular orbitals, psi A plus psi B. And one more type of interference is also possible, that is destructive interference. So during destructive interference, the amplitude of the electronic waves of both of these atomic orbitals get cancel each other and finally produces very less electron density in the molecule. So this is called as psi A minus psi B. This type of atomic orbitals are known as the anti-bonding molecular orbitals. So here we can understand clearly that the intermixing of atomic orbitals to produce the molecular orbitals can take place in the two ways. When the in-plane interaction takes place, means both electrons are in the same plane, so that interference will be stronger. Such interference is called the constructive interference, that increase the electron density in the molecule. So that type of the orbitals are called the bonding molecular orbitals. And if both are in the different planes, see here plus is there, here minus is there, so they cancel each other. So the number of electron density in the molecule decreases. They are called the anti-bonding molecular orbitals. That means it clearly says that wherever electrons are maximum, that molecule is more stable. So that bonding molecular orbitals are more stable and anti-bonding molecular orbitals are less stable. Stability also associated with the energy. Lower the energy, higher the stability. That means since bonding molecular orbitals are more stable, they possess the lower energy than the atomic orbitals. And these are less stable because less electron density is present. That's why these anti-bonding molecular orbitals are less stable and having the more energy than their respective atomic orbitals. So we can see this one by taking a small diagram. So let us take orbital. Let us imagine 1s orbital of one atom intermixed with the 1s orbital of the another atom. This is energy axis. So when they are intermixing, two type of interactions. One is additive interaction. Second one is subtractive interaction. These are called the molecular orbitals. In these molecular orbitals, this is the average energy of the atomic orbitals. So molecular orbitals has a less energy than the atomic orbitals, whereas other orbitals are having the more energy than the atomic orbital. They are called the anti-bonding molecular orbitals, and these are called the bonding molecular orbitals. Usually bonding molecular orbitals are given notations sigma, pi, delta, etc. Anti-bonding molecular orbitals are given notation sigma star, pi star, delta star, etc. only to differentiate the bonding molecular orbitals from the anti-bonding molecular orbitals. So in this way, here these orbitals are formed by overlapping of psi a plus psi b, additive interaction, and these are formed by subtractive interaction of the atomic orbitals. Now the question arises, why bonding molecular orbitals are even more stable than the anti-bonding molecular orbitals? So whenever atomic orbitals are intermixing with each other, we can see these interactions. Let us take the s orbital and s orbital. Two type of attractions takes place. When they interacted in a positive way, we get the bonding molecular orbitals. When they intermixed in opposite way, we get the anti-bonding molecular orbitals. In case of bonding molecular orbitals, electron density, already we have seen the diagram. Electron density between the both of this nucleus gradually increases. When electron density increases between the nuclei of the molecular orbital, we know that nucleus carries the positive charge, electrons carries the negative charge. So these negative charged electrons reduce the repulsions between the both of this nucleus and gives stability to the bonding molecular orbital. And in case of anti-bonding molecular orbital, these are the nucleus. In case of anti-bonding molecular orbital, you can see that electrons are present away from the both of these nuclei. That causes a nodal plane between the both of these nuclei. There is no electron density between the both of this nucleus. As a result, there is nothing to reduce the repulsions between the both of this nucleus, which gives an instability to the anti-bonding molecular orbitals. So that clearly says that the presence of electrons in bonding molecular orbital gives stability to the molecule. The presence of electrons in the anti-bonding molecular orbital gives instability to the molecule. Reason is, in case of anti-bonding molecular orbital, electrons still try to go away from the nucleus so that they give the instability to the molecule. So that number of electrons in bonding molecular orbital, if greater than the number of electrons in anti-bonding molecular orbital, such type of the molecules are said to be stable. If number of bonding electrons less than number of anti-bonding electrons, or number of bonding electrons equals to number of anti-bonding electrons, such type of molecules are said to be unstable. Now let us see the here. One is s orbitals are intermixed. So when s orbitals are intermixed, whatever the molecular orbitals are formed here, these are called as sigma 1s orbital or sigma s orbital. I am taking 1s here. So that sigma 1s, and this is said to be sigma star 1s. And if you take the p orbital intermixing, Imagine z-axis along the z-axis. If both p orbitals intermixes in the same plane, again we get the two type of the molecular orbitals. These are nucleus. Plus minus. So these are nucleus. So this is called the sigma p orbital. This is called a sigma p orbital. Usually as per IUPAC convention, we take the pz orbitals undergo intermixing along the internuclear axis. So let us take the sigma 2 pz orbitals. So here also we can write down the sigma 2 pz and sigma star 2 pz orbitals. In case of the sigma orbital, there is no nodal plane, but in the case of the sigma star orbital, one nodal plane is present. Now let us take the pi orbital formation. Both px and py orbitals are said to be participate in the pi bond formation. That means px with px, py with py. Anything you can consider here. Let us take the 2 px orbitals and 2 py orbitals. So here we can get the nucleus, pi bond formation, plus and minus, and here we get its respective anti-bonding molecular orbital, plus minus and plus, nucleus is present. This is called the pi star orbital. So here one nodal plane is present along the internuclear axis. Here two nodal planes are present. So if you observe these molecular orbitals and anti-bonding molecular orbitals, we get one more information that number of atomic orbitals intermixed is equals to number of molecular orbitals produced. But here we get the two atomic orbitals intermixed, so that we get the two molecular orbitals. In that, one is bonding molecular orbital, one is anti-bonding molecular orbitals. That means half always belongs to the bonding molecular orbital and half always belongs to the anti-bonding molecular orbital. Now if you observe here, both bonding and molecular orbitals are of two categories are there, sigma orbitals and pi orbitals. In case of all sigma orbitals and sigma star orbitals, you can see that these are all symmetrical. Sigma orbitals are said to be symmetrical and pi orbitals are said to be unsymmetrical in nature. The reason here is, if you observe along the internuclear axis and here also along the internuclear axis, upper side and lower side same amount of the electron density with the same sign is present. See, plus is half and plus is down, and minus is half upper and minus is down. In this case also sigma orbitals and here are sigma orbital. That means sigma orbitals are said to be symmetrical around the internuclear axis or bond axis. That means they are said to be symmetrical. What about the pi orbitals? Pi orbitals are not symmetrical around the internuclear axis. You can see that along this internucleus, above positive sign is there, here negative sign is there. Here plus minus, here minus and plus, opposite signs are there. So that we can say that sigma and sigma star are symmetrical around bond axis. Both pi and pi star unsymmetrical around the bond axis because of the presence of the different sign, plus above and minus below the plane of the bond axis. And what about the number of nodal planes? Sigma orbitals don't have any nodal planes. Sigma star orbitals are having the one nodal plane perpendicular to the bond axis. Pi orbital, one nodal plane is there. Pi star orbital, two nodal planes are there. So that we can write down that sigma, no nodal plane. sigma star and pi orbitals, one nodal plane is present. Pi star, two nodal planes are present. So this is the theory part of the molecular orbital theory along with the linear combination of atomic orbitals. Dear students, I hope you understand this class. Do like my videos and subscribe the channel. We shall meet in the next class. Thank you one and all.